Good morning, welcome to my laboratory. What you're looking at here is the trace from the probe calibrator of my 2213A Tektronix oscilloscope. And right now the probe is set to 10x attenuation, and the channel coupling, which you can't see, is set to DC coupled. And there it's set to ground. So you can see that the baseline is right on the center radical marker. And when I set it back to DC coupled, you can see that this is actually a negative going square wave pulse. But notice something here. The pulse is not perfectly symmetrical with a 50% duty cycle. The tops of the square wave is a little bit shorter in duration than the bottom of that square wave. Okay? So now when I switch to a slightly higher magnification and go from ground to AC coupled, the AC coupling moves the average of this trace to the center radical marker, or the zero baseline reference. But since the trace is not symmetrical in terms of time, it goes to a slightly higher voltage on the upside than it does on the bottom side. You see that? This is about just barely a little over 1 minor division, and this is fully 1.5 minor divisions up there. So it's a little bit higher up here than it is down here. So the voltage appears asymmetrical, but the area of that slightly higher lump, since it's shorter in time, is the same as the area of that slightly lower hump there. So the AC coupling feature has indeed moved the average of this baseline to the average of this signal to the zero baseline that we positioned with the vertical position control to set it on the center radical marker. Okay, now I'm going to turn the amplification down and switch the probe to 1x attenuation. Get back in there. Okay, now in the 1x attenuation, I think you can see that there's a little bit of a slope to those lines. Let me get it at a little bit better time base there. Okay, you can see that the lines aren't perfectly parallel with the radical lines. They slope a little bit, and that's pretty evident if you get it at a magnification like this. Okay, so what happens if I switch to DC coupled now and move the trace down to where you can see it? See, that sloping goes away now. That's an effect of the AC coupled input coupling. And here's another thing. If I have the probe set at the the channel input set to AC coupled and the probe set to 1x attenuation, now if I use my little screwdriver to adjust the compensation capacitor in the probe, I get almost no variation in the shape of that signal. You can't see me doing it because it's over here. Okay. But if I switch the probe to 10x attenuation, and then display that at a reasonable amplitude, now when I turn that compensation capacitor, you can see a large change in the shape of the signal, the displayed signal. And what I want to do is turn that capacitor to where I get the squarest possible or flattest possible shape, like that. Now the probe is adjusted properly. Once again though, if I switch now to 1x attenuation and leave it on AC coupled, you can see that it has that downward slope or upward slope like that. In the DC coupled condition, it's nice and flat straight across. Okay, so most of the time when you do measurements with the scope probe, you want to use 10x attenuation. You want to have that compensation capacitor adjusted properly, and you'll be using DC coupling to get the best looking trace on the screen. With AC coupling, the average of that trace moves up to the center gradical line, but you have to be careful about the symmetry, the time symmetry of the traces. Otherwise you might be thrown off by the fact that the amplitudes look a little bit different, top and bottom. Thank you for watching.